Hello, the goal of this video is to give an interesting result about Aumann expectation that connects it with the support function that we defined in the previous lecture, in the previous video. So I want to start first with some reminder on conditional expectations and conditional probabilities, because I want to expand a little bit the discussion here about Aumann expectation to conditional expectations. Now, the thing that we talked about Aumann expectation will transfer to the conditional, because you can think about a random set as a collection of random variables selected from the random set. Okay, and the Aumann expectation is the set of all the expectations of those selections, those who have finite expectation. And therefore, the conditioning will transfer to the Aumann expectation, the conditional Aumann expectation will transfer to that concept, because we will look at the conditional expectation of the selections, and then we have the definition for what is conditional Aumann expectation. So let's give some details. So we start with the probability space, omega, the sigma algebra F, and probability measure P. And let's first think about what does it mean to have here a random variable or a sigma algebra that is induced by a random variable. So let's look at a random variable x, okay, which is always a mapping between omega and Rd, and I want to focus just on R now, and R is equipped with its Borel set. And it's an interesting random variable such that x, okay, is equal to 0 with probability p, and 1 with probability 1 minus p. And what does it mean? Okay, so let's give a little bit more details here. What exactly this random variable means? It means that there is omega naught, subset of omega, which is in the sigma algebra, okay, for which the measure or the probability of that omega naught, okay, is exactly small p, okay, and also the x here will be such that x of omega, okay, is going to be equal to 0 if omega is in this omega naught, okay? And it's equal to 1 if omega is in the complement, which has to be also in the sigma algebra, okay? And we can write this omega 1, okay? We can call the complement just omega 1. So what we created here is a partition of omega, okay? And it means that omega naught intersection with omega 1 is the empty set, okay, they don't overlap, and the union of omega naught and omega 1 is everything, okay. So we divide the omega into two parts, and small omegas that fall in this part of the partition will result in a 0, and omegas that fall in this part of the partition will result in 1. Okay, so what will happen here is that we can define another sigma algebra. I can call it, let's say, F naught, okay, which is just the empty set that always has to be there. Omega naught complement, which we called omega 1, okay, and everything is omega. It also has to be. Okay, so it's much cruder sigma algebra than F, and we could start with F naught, this F naught, and define the random variable x on just this sigma algebra. Okay, so we could have this probability space. Okay, and there will be just this random variable there that is defined, and that would work as well. Okay, so this is the sigma algebra induced by the random variable x. Okay, so now what will be a conditional probability? Okay, so we want to define suppose we have another random variable, let's call it y, which is also defined from omega to r, okay? And it could be to rd, but let's stay with r. And y, what is the probability, or how do we define the probability of y, okay, given x, okay? So we could write this actually without specifying the x, okay, if we add this sigma algebra or any sigma algebra which is a refined, is a cruder sigma algebra, is a subset of f, okay, so we ask ourselves, what is this, okay, we could also ask ourselves, what is in general y conditional on some f naught, okay, for some f naught, which is a subset, okay? It's a sigma algebra itself, okay, but it's a subset of f, okay, for some a sigma algebra. Okay, what is this? We ask ourselves, okay? So here, okay, and that's a more common way to write things, okay? We create a sigma algebra that is induced, or we think about a sigma algebra that is induced by x, and so on. So we can write it like this, but we can think about it in a more general way, as we have some sigma algebra which is a subset of the original sigma algebra, the more refined sigma algebra, and what does it mean to think about something like that? Okay, so it is basically asking, okay, that to be more specific, okay, take some event b, okay, which is an element, a measurable event in f naught, okay, and take some a, which is in f, okay, some set of values that y could get, okay, because y is defined on this probability space, okay, and we ask what is the probability, okay, this kind of events, okay, is basically y in a conditional on x in b. Okay, that's basically what the question is asking here. Okay, that's the nature of this kind of probabilities, conditional probabilities. Okay, so let me move up here. I'm running out of space here. We know, okay, so this probability, okay, let's write it again. The probability of y in a given x is in b. Okay, and b is from f naught, and a is from f. Okay, it's equal to the probability that a is in intersection with b over the probability of b. Now, how do we know that those two are well defined? Okay, they are well defined because a intersection with b is, because b is in f naught, so it's in f. So this intersection has to be also in f, and again, b is in f. So those probabilities are well defined, so we can write this ratio. And of course, we need to take care of the problem that b might be equal to 0, or this probability might be equal to 0. So that's not something that is allowed, but we need to take care of that. But let's stay with a simple case here, and that's the definition, okay, and everything here is well defined, okay. So that's the conditional probability. Similarly, we can think about conditional expectation, okay, the expected value of y conditional on the sigma algebra, which will mean that we want x to be in b. Okay, so it will be the integral of y with respect to this probability. Okay, and that's the meaning. Oh, I need same bracket here. Okay, that's the meaning of conditional expectation, and again, we can write it like that, and we could also think about conditional expectation given the refined sigma algebra, which means that we can define. Okay, so if we write it like this, okay, let's write it like that. Okay, if we have this, we mean that we are going to compute this expectation for any possible event in F naught. Okay, and that's the meaning of this notation. This is actually by itself a random variable. Okay, because after the condition we can ask, okay, if we can evaluate it in every omega, and that's a random variable by itself. Okay, so this is just a reminder of what is conditional expectation. So now we want to move to the result related to random sets, okay, that uses all this language. So let's look now at this probability space and a random set defined on this probability space that gets its values as closed sets or closed subsets in RD. So first of all, in order to get a result about the Aumann expectation, it's taking support function of an Aumann expectation and so on, we want to establish or use the fact that the Aumann expectation will produce a convex set. In order to do that, let me also here take a small detour and mention that we have to have, or we have to assume that this probability space is non-atomic. Okay, so the probability space is non-atomic, but I want to condition on a sigma algebra F naught. So the probability space we'll say has no F naught atoms, okay, if for any A in F, okay, the original one, okay, such that P of A conditional on F naught, okay, which is another sigma algebra, okay, is positive. Okay, so if we find A such that its conditional expectation, probability is positive, okay, then we can find a set B also in F, a measurable one, okay, such that the probability, okay, of B, okay, conditional F naught is less than the probability of A conditional on F naught. In other words, we can, if we have A that has a conditional positive probability, we can find another set B, okay, in the sigma algebra whose probability measure, conditional on F naught, will be in between this positive number and 0. Okay, so there is no jump from this probability straight to 0. There is always something in between. We can find a set, smaller set, such that, smaller in a sense of probability, such that this probability is less than this probability. Okay, so there are no atoms. You cannot find even, let's say, the most striking example is that there is one small omega that gets a positive probability, and there is no subset of it except for the empty set, which gets probability 0. Okay, and it gets that specific omega gets a positive probability. That's like an atom. This is why it's called non-atomic. There are no such sets that you cannot divide its probability, its positive probability, and find something in between that positive number and 0. You can always find something in between. And even between B, okay, and the 0, there will be another set C that will be somewhere in between this 0 and this positive number, and so on. Okay, so it's non-atomic in that sense. So again, I just also think that when I write here set, it's not clear, but it means that we will think that X, okay, this random set the probability that it hits or intersects with A is positive, then this probability can be split when we find another B for which X intersects with B, and that's going to be also positive, and so on. The reason why we are looking at this sigma algebra is that we are going to condition on we want to think about expectations or regression, conditional expectation, which is a regression. We will condition a bunch of covariates. And one way to achieve this non-atomicity, okay, with respect to the sigma algebra, is that one of the covariates that we will condition on as a continuous distribution. If that is true, if we have at least one variable covariates that has a continuous distribution, then it's fine. That this will be satisfied. Okay, it's not necessary, but it's sufficient to have that. Okay, so let's see now what is the result that we want to establish with respect to the Aumann expectation and the conditional Aumann expectation of this random set conditional on this sigma algebra. Okay. Okay, so let's connect between the Aumann expectation and the support function. Let's take a random set. Okay, so assume that X is a random set on omega f p, okay, and X is integrably bounded, okay, bounded, which means that is cell 1, okay, is non-empty, and cell actually is equal to cell 1, so all the selections have a bounded expectation, okay. Let F naught, which is contained in F, be a sub sigma algebra. Let's say sigma algebra, and the probability space has no F naught atoms. Okay, in the sense that we explained before. Okay. So if this is the case, then okay, let's write it here. Then 1, the Aumann expectation of X given F naught, okay, which is the set of all expectations of X given this F naught, again in the sense that we explained before, such that X is in cell 1 of X, of capital X here, okay. So it's all these expectations, okay, is unique, non-empty, convex set. Okay, so that's the first thing we can say here. So basically, the Aumann expectation definition extends to conditioning. Okay, and it's a convex set. Okay. 2. Okay, and that's an interesting result, or the most important result with respect to Aumann expectation, and a very important tool that we can use in the future, is that if we look at this Aumann expectation, okay, conditional on F naught, okay, and we take the support function of it in a direction u, okay. In order to compute that, we need to compute the Aumann expectation, and that might be complicated because we need to look at all the selections. That's a lot of stuff there, okay, that can be challenging. But we can reverse the order of support function and expectation in the following way. We can look at, okay, the support function of x itself, okay, and we can now, sorry, we need to do that in a certain direction. The same u here. Okay, let's look at this support function, and we will take the usual, okay, because that will be now a random variable. When we fix a u, that will be a random variable. Changing the omega will give us a different set. We can take the support function of it in the direction u, so that's going to be a random variable. And again, by the definition of what is measurability with respect to random sets, that makes sure that this entity is indeed a random variable. And we can take the expectation of this conditional on f naught. So that's a regular expectation, because this is a random variable, okay, and we can take the conditional expectation of that random variable, of this random variable, conditional on f naught. Now, what's the advantage of doing that? X itself can be a very simple set. Maybe we saw some examples in which x could be just an interval, okay, the y lower, y upper, or it can be just one point, or it can be just a discrete number of points. The support function of x can be a very simple thing to compute, okay? And then we just need to take regular expectation of this random variable, whatever comes out of this, which again may be very simple. If it's an interval, it's just the endpoints, or one of the endpoints, a maximum between those endpoints, and their multiplication with u, okay? So that's just two numbers, and we take a maximum, we take expectation of that, and that can be relatively to this entity, that might be easier to compute, okay? So the fact that we can change the order of expectation and the support function can be very handy, okay? So that's the result, or the important result, that connects the Aumann expectation and the support function that we can use later on. Thank you for watching.